I hope we don't get to the day where you guys literally need music just to listen to someone talk. That would be really sad. So far, we're already like, you need music to pay attention and to do homework and to get any productive work done as well. But hopefully we can still listen and have relationships and learn from people auditorily. I have tried like music during passing periods and whatnot, but the problem is I don't have it set up easily to be able to do such. Because like my microphone is on my phone and then the music would be He also knows a lot more. That's because he was fine in college. Anyway, so not in a bad way. Not in a bad way. He was just like the nerdy, like he would go to their boyfriend on the weekend. But it's really cool because I think all of them are currently in leadership, like church leadership, as far as worship pastors, and a few of them are still like professional musicians, but they're all like it's just God's using them really cool. Anyway, here we go. You guys did an awesome job because question: why was the limit 2?
There's a hole.
It's all about the approach. So, what was I trying to show you in all those tables yesterday when I was doing things like crossing off the in-between and crossing off the in-between and crossing off the point and saying it's not necessarily about what's going on at one. A limit answers the question of what's going on as you approach one. I was leading you up to this type of question. To say a limit talks about the approach. So the value of the function might not exist like this hole. I'm going to go ahead and erase the X just to make it very clear. There is a hole there. The function does not exist there. But a limit answers a very different question. And sometimes the limit is the same as the function value. Sometimes they coincide. But they do not have to. And in thinking about limits forming the foundation to calculus, calculus is answering, in a sense, the impossible questions of what we couldn't do by hand. And so we don't want to be concerned with what's going on at a certain situation, or mathematically speaking, whether or not it exists. We want to talk about the approach because that's what makes the calculus possible. So once again, the limit was 2 because we were looking at the y value that the function was getting closer and closer and closer and closer and closer to. And if we were to go into our calculator and plug it into a table, it wouldn't matter that the hole is at 2. What matters is that the approach still agrees from either side, whether from above or below, they're going the same direction. Now, the fun thing is, we're going to learn today when the limit does not exist. And some of you have a very specific moment and a very specific meaning that made all the difference. Whether or not she actually she was just remembering some guy's hair. In the back of the board had an answer written and she realized that. Anyway, so the limit as X approaches 2. It's like, no, the whole point is that girls can do math, but you just said that. Sometimes it defeats the purpose they were trying to prove if you actually know that. But anyway, that's right.
Zero solved.
No party. It's so free. Anyway, so Mrs. Dash. Here we go. So question, kiddos, what would you do on this example? Don't necessarily. Pretend that the dashes are a little bit off in the sense of where they are. It is always dangerous to trust the picture, but that's 12, that's 10, that's 8, that's 6, that's 4, that's 2. How do I look at this picture? We're not doing algebra, we're not doing equations. We're looking at the graph. How do I approach this picture? Look at the hole, but why the hole?
X approaches the limit.
Because it's the limit as x approaches 2. So as x approaches 2, right? X value approaches 2. But I can't keep my head in the sand. I can't keep it down here. I have to look up to the function. The function, at all these values, leading up to 2, isn't it up here on the line? And all the values past 2 coming down, isn't it on the line as well? So even though I am going as x approaches 2, I'm looking up to the function, and I'm saying what's going on is these points get closer and closer and closer and closer, and if I keep on going, closer and closer and closer and closer, and similarly closer and closer and closer. What am I looking at? What's the answer to a limit? What kind of value? A y value. So I'm looking at where is it approaching, where is it approaching, not necessarily caring what it's at, and what is it approaching? 12. So my y values are approaching 12, my y values are approaching 12, so the limit, I want that arrow, the limit is 12. Now let me ask you a different question, right? What if I was to ask you, let's see if that confuses anyone. The limit of the same function, 3x squared minus 12, all over x minus 2, as x approaches. Any other nice values? Negative 4. What would that change? Where I'm looking changes. So now I'm looking where on my function? Wait, there's nothing there. Hold on, what kind of function is this? It's a line. Are you going to keep on going? Yes. So can I approach from either side? Yes. And as I approach from either side, we can go ahead and think about it. Demonstrate. Is there a hole this time? Wait, who cares? Where am I approaching? Yeah, approximately negative 4. I might be marked a little bit off. But approximately negative 4. So as the x's are approaching, you guys getting that we're going to the function and looking? As we're going to the function and looking, the y's can be approaching negative 4. Okay. Once again, this is foundational. Don't worry, it'll get harder. So when don't limits exist? Let's start with the most basic. And I would even say the most important. Time when limits do not exist. Most basic. I would say even the most fundamental example of when a limit does not exist. As x approaches a. So I've made each of these graphs with an a at a different, sometimes the a is a positive, sometimes the a is a negative. I just made different graphs with a generic a. A could be 1, a could be 4, a could be negative 10. Who knows? Each of these graphs have an a marked and have a function. There's a certain behavior above or to the right, a certain behavior below to the left. And the question for limits are, do the one-sided limits agree? So there are 2 technical ways a limit does not exist. The most important one as far as even what the AP expects as far as the answer should be D any of the limit does not exist. Mostly revolves around this first one that we see right here. It says the limit does not exist when approaching from each side yields different results. Now hold on, every limit problem at its core, what's the motion going on? What's going on? X is approaching A. So when I say approaching from each side, I mean from above A and from below A, right? From above A and from below A. Yield different results as far as different y values. Do you guys see the different y values? From above in a table, this would be approaching, 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 approaching this y value right here, which we could call, I don't know, C. But approaching from below, this direction, I would get D. Does C equal D? No. Does the limit exist? No. So the proper way of answering this question would be the limit. Now, why don't I write equals? I suppose you could write equals. Why is that awkward though, if you think about what it means?
Because there would be that equal.
Yeah. The limit does not exist. Well, that's just awkward to say. But if you just say, what is the limit? The limit does not exist. That makes a little more sense. That's why I don't really write equals. But if you do see equals, don't get super mad about it. The limit does not exist. You have to think about what D and E actually means. The one-sided limits do not agree. Now there is another case when the limit will not exist, and I'm going to put that in air quotes. Because the limit at its core, the informal definition that we talked about said, y is approaching a constant L. Y is approaching a constant L. I want you guys to go ahead and look at each of these graphs. Starting with the first one though. Let's go ahead and zoom in. As I go from below and above A, remember, I don't really care what's going on at A. I don't really care there's a vertical asymptote, except I do care what a vertical asymptote means. That means the graph is skimming it forever, going to, what's the behavior as I come in towards a vertical asymptote? Either the graph is going infinitely high or infinitely low. Is it going to a constant? It's not going to a constant. Now technically, I don't care that it doesn't touch. What I do care, because all I care about is the approach, what I do care is that it's not actually going to a constant. So I'm going to say DNE for this one. Because technically, the limit as that's approaching a constant is not happening. It's going forever high. But the idea, wait a minute, but where it's going, where the y values are going, do they agree from either side? That's a yes. They do agree from either side. They're both going up. So even though the limit technically does not exist, we still answer this one and we say the limit is positive infinity because that is where, from either side, the function is going. So we still express it as an answer. In writing positive infinity, we are saying the limit as a constant technically does not exist. But we are still saying, hey, from either side, from above or below A, they're both going infinitely up. So we say the y values are approaching infinity. Which we've done that before. Didn't we do that whole like y values are approaching infinity when we were talking about behavior of vertical asymptotes? We're just using it now to answer a limit question. The question, what would be the only possible way to answer the second graph? There is a horizontal asymptote, you're right. There is a horizontal asymptote. And there is a vertical asymptote. But technically the horizontal asymptote has nothing to do with the question. That is a characteristic of the graph. It has nothing to do with the question. The question is totally concerned about as x approaches A, where are the y values of the actual function headed? The struggle is wait a minute, from below, those y values are headed to negative infinity. And from above, the y values are headed to positive infinity. Read A again. What does A say? The limit does not exist when approaching from either side gets you different results. Do I have different results? As I approach from above, in my table, the city going to bigger and bigger and bigger, probably like E with 99 after it. Bigger and bigger positive numbers. Scientific notation will probably come into play. This one, going lower and lower and lower numbers. Not lower as in magnitude, lower as in sign, aka negative infinity. Negative scientific notation will be involved. So, if I'm coming from above positive infinity, below negative infinity, well, question, what is my limit? The only way I can answer this question is the limit does not exist. So even though this one, okay, we'll say infinity technically is not a constant, but we still express an answer if they agree. But A trumps this whole like, still express it as a infinity, as uninfinity, I should say, I apologize. Because if approaching A from either side, or I should say from both sides, yields a different result, the results do not agree, the limit does not exist. You'll hear that one. If the one-sided limits do not agree, the limit does not exist. And we actually haven't defined one-sided limits, but maybe you guys understand it coming from one side and the other. Last but not least, this one's weird. I want you guys to get your graphing calculator. I want you to actually graph the function that you see in the example down below. But write it down first. If the graph oscillates between two fixed values as you approach, remember, the approach x approaches A. There's some motion going on. There's some situation. X is approaching give out like the classes. This graph at first doesn't seem that bad when you graph it your graphing calculator. Like, ooh, the answer is 0. You guys to actually graph this function. You could go in your table and you could do 0.01, 0.001, 0.0001, negative 0.01, negative 0.001, negative 0.000001. Yes, I have tons of extra heritage headlines because Algebra 1 didn't really care. Well, plus they weren't really paying attention and I didn't remind them they were there, but they really didn't from yesterday, grabbing them over the light reading and or just picture looking. Anyway, so good stuff to read those. I'm going to go ahead and throw this into my graphing calculator also. Oh, unless I don't have my graphing calculator, that's very sad. Let's go get it. Sine of 1 over x. I would say in radian mode. You could go in degree if you would really, really like to. It doesn't look that bad at first. You're like, oh, it's not that bad. It's just going to 0. If you look in, without zooming in, like zoom standard. Ooh, hey, a derivative. Let's get rid of that, though. Okay. Oh, no, wait. I'm in zoom, not standard. There you go. You guys know how to stop your calculator if you're like, oh, no, wait, don't graph yet, right? You hit on, yeah, on breaks it. Enter just pauses the graphing. It doesn't get you out of it. On though stops it and says, wait, what? You need something else? Anyway, it doesn't look that bad. Maybe even if we zoom in, it's still not all that bad. You're like, oh, it's going to 0, right? Like, oh, okay, it's going to 0. Did you guys keep zooming in like I told you to, though? Now it looks like positive and negative infinity. Now it looks like I'm not even really sure what. Now it looks even, maybe even, okay. Now some of you are still like, but isn't that still a 0 or a barcode or something? Anyway, if we were to go ahead and plug in 0, does 0 work on the curve? No. So the function doesn't exist. Is it a hole? Is it a vertical asymptote? I don't know. Keep zooming in, but it keeps on just getting worse. Now you could try going to your table and saying, but Miss T said we could use a table. Okay. So if we were to use a table, now I'm going to go by irregular steps. Because if you go by regular steps, you see a pattern. And it is a pattern for those regular steps, but go outside those steps and it gets a little weird. Meaning, I'm going to go 0.01. Then I'm going to go negative 0.009. Then I'm going to go negative 0.000013. Then I'm going to go negative 0.00000001. Question. I'm getting smaller, guys, but what is this thing doing? It's like at almost 1, and then it's at like a half, and then it's at like 0.4. It's just going up and down and up and down and up and down between like 0 and 1, and I haven't even, well, I'm giving you negative 1 and 1. But if you go the other direction, guess what? It's going to be equally as confusing. I don't see any convergence. Now, they're small numbers, yeah, but I don't see any convergence. I don't see it getting infinitesimally close. And guys, 0.000000, I'm pretty stinking close to 0, right? This thing, yeah, no. The limit does not exist. It rarely happens. I have to show you calculus as to why. We'll just say for right now, the limit. So, answer the question when a limit does not exist graphically. Yeah. Okay. Let's see if maybe it makes a little more sense.
Let's solve the problem.
Oh, we should, Mo. We should sue. It worked last time. Look at you guys knowing how to be sneaky.
That's not being sneaky.
Okay, well, that is a very dangerous statement to make. So just.
Contestants, find the limit of this equation.
Calling somebody else fat won't make you any skinnier. Calling someone stupid doesn't make you any smarter. And warning Regina George's life definitely didn't make me any happier. All you can do is try to solve the problem in front of you. The limit is -1. Oh crap.
That answer is incorrect. We are in a sudden death. Miss Heron can answer this problem correctly. We have a winner.
Limits. Why couldn't you think about anything about limits? Limits. That was a week Aaron got his haircut. Oh god, it was so cute. Okay, focus, Katie. What was on the board behind Aaron's head? If the limit approaches anything, the limit does not exist. The limit does not exist.
Our new state champions, the North Shore.
You guys see the function? Throw in your calculator. See what it looks like. Go. Limit as x approaches 0 of ln of 1 minus x minus l pass over 1 minus cosine. Oh, yeah, you really can't see fingers. ln of 1 minus x minus. Ooh, is it sine or sine squared? That's a good question. Hold on. There we go. Sine of x. Yeah, it has to be. The struggle is in order to actually be able to solve this without graphing. Cosine of x in big parentheses with a squared on the outside. Don't get tricked by the trig notation. Yeah, big parentheses are on the whole cosines. Or on the whole cosine. You have to do a parenthesis before the cosine and a parenthesis after the cosine.
Actually, she's correct.
Wait. Nothing's happening to mine.
Zoom like 6.
Now here's the real question. Was she able to actually visualize this? Probably not. Yes, she was. Okay, whatever you said. Because without being able to do that, she would need Calc BC, Calc 2. Well, she could have used L'Hopital's, but that wasn't being taught when this movie was made in Calc AB. So, anyway, it's a little questionable. It's a little questionable. But if she was able to visualize it, you would need to know derivatives, sadly. But let me go ahead and unfreeze real quick. I don't even know what zoom in. Oh, I mean like zoom in, zoom in, zoom in. That's not going to work. What did you guys say? Zoom did work? So she actually, at least they had something on the board that did apply. I'm just really not sure she could have visualized that graph.
I believe in the power lines. I believe.
I still think they disproved that she remembered
Her boy crushes what she thought about more than anything else. Okay. So, I think she was Calc AB. Like from the questions that they did, It didn't seem like they had done BC, but I don't know. If she was in BC, then maybe she could have done that.
I'm so sad.
We'll peek at them in the fall. Alright, cool kids. So anyway. How do we do this guy graphically? Okay, he's not as bad as the one that we just saw. Do we know anything about this guy? Could we do this by hand? Could we do this on a calculator using booleans in the pre-calc graphing calculator handbook from the beginning of the year? Yes, with a little division sign. Beginning of the year, you're gonna remember which one. So, how could we do this one by hand? Let's have some fun with it. We know that 2 is important, right? Okay. What's going on before 2? Before 2. Does this make sense that this is the from below? Why is this the from below piece? Exactly. Right? And then this bottom one then would be from above. Right? Because I'm above 2. And that helps me with graphing if I think from below from above, because I can say, okay, from below, let's just ignore for just a second. Let's ignore this part of the graph. That part of the graph doesn't matter. All I care about is what's going on this side, which is why I'm going to look at this function. So how do I graph negative 2x, cool kids? Y equals negative 2x. What is that?
It's a line.
It's a line with an intercept at 0, 0, because it's negative 2x plus 0. So b is 0. What's my slope? That's one way.
It's a slope of negative 2.
Down 2.
Slope of negative.
Is that okay?
And then up
So I could go down 2 over 1, and I could go up 2 just back 1, right? So then I could go ahead and say, all right, I know that this function looks like, and then looks like, and then where would it be at 2? Because we're equal to, so you keep going.
yeah, negative 4.
Good. It would go down to negative 4, yeah? And then it would go over 1 more, and then I'd have my other point down here. I'm going to fill that in. Okay. So there's one piece of my piecewise function. Now, kiddos, what am I going to do in order to get the other piece of my piecewise function? Kind of. Negative 4 cut in half is 2. 2 squared is 4. So I can add 4 and subtract 4, and I can say that's x minus 2 quantity squared minus 3. How does that help?
Well, you go down 3.
My vertex. Not here. Oh yeah, I can go down 3 and right 2.
Then right 2.
Because my vertex is going to be at 2, 3, HK. I can think of this as y equals, right? I can add the 3 to the other side if that helps. My vertex is going to be 2, 3. No, 2, negative 3. Sorry, I didn't write the negative in my vertex. 2, negative 3. And then I guess I can find a 0 if I really wanted to. Is this going to be a concave up dude or a concave down dude? Good, because the sign in front is a positive, right? Concave up, like a cup, like a smile, a positive person. Or even positive people up there. Question. Then, as a result, I didn't actually write the limit question. I was just seeing, first of all, if you guys could get the graph. The limit question, what if I was to say the limit as x approaches, uh-oh, my line got kind of slowed down. What would the limit be as I approach 0? What would the limit be as I approach 2? And what would the limit be as I approach? Let's do one more. 3. What do you guys think? Zoom in just a little bit. What's the limit as I approach 0, first of all? Is it really that easy? Yeah. Because 0 isn't 0 less than 2? So don't I only care about what's below? So don't I only care about this guy? What's going on as x approaches 0? What are the y's doing? Approaching 0. So I can go ahead and say, yeah, the limit is 0. And what if I'm taking the limit, let's go ahead and skip ahead to 3. Can you skip to 3? What's the limit as x approaches 3? Am I looking at this piece? So I'm looking at this guy. So I want to know what's going on at 3. Wait, pause. Okay, hold on. Maybe we don't have to keep our head stuck in the graph. How can we figure out wherever 3 is, right? I could mark down and say, okay, wherever that is, that's going to be a point on the graph. So as x approaches 3, what are the y's going to be approaching? Something. Isn't it going to be approaching what's there? That's cheap. I know we don't care about what's there, but isn't what's there going to be what's there? Right? It's approaching this point. How can I find that point? Plug it in, plug it. Ooh, now you guys are getting ready for section 12.2. Plug it in, plug it in. Plug it into what? The top piece or the bottom piece? Bottom piece, because it's above 2. So I'm going to go ahead and plug in and say, okay, let's plug in 3, and it's going to be 3 squared minus 4 times 3 plus 1. Let's see how, remember I just kind of randomly put a concave parabola. It's going to be 9 minus 12 is negative 3 plus 1 is negative 2. So maybe, even though we don't really care what's going on at, it's more about the approach, maybe the at can sometimes help. So maybe I can sometimes just plug in. Now let's go to the hard question. Maybe it's the easy question, depending on your brain. What's the answer to letter B? Why? As you approach from either side. The limits do not agree, so the limit does not. Why? As x approaches 2. My function approaches 2 very different places.
Why is c negative 2?
Well, remember I randomly graphed this parabola? I was like, oh, I don't know, something up. So then in order to make it very precise, we went back to the function and we said, hey, the limit is approaching the point that's there, so let's go find the points that's there. So we plugged it in, And when we plugged it in, 9 minus 12 plus 1, or 10 minus 12 is negative 2. Okay, what would you guys do for this one? Ready, set, go. Use your graphing calculator. I'm not even going to have us, yeah, we're good. We don't need it. And we're not going to learn how to do this with algebra until section 12. So you guys are going on with 2. Do you guys see where the limit's approaching? 4. Good. Just in case I'm blocking your view.
Was it how you put the fraction again?
Ooh, alpha, y equals, hit enter. That's n over d, it makes the little fraction you do. So I'm looking at 4. Uh-oh. Uh-oh. What's going on at 4? Maybe the equation shows me as well. At 4, I have a denominator that would not exist, and I think I see a what?
Vertical asymptotic.
So what's the limit?
4.
Because as they come together, as you approach, do they agree? They infinitely do not agree. 1 and a 2 and a 3 and a 4. Where is it coming in? It's coming in from like here-ish. That's coming in from here-ish. Yes, the limit does not exist.
Do you care at all about the horizontal asymptote?
Not as we're coming to 4. Because
Because as we're coming to 4, we're not going out there. We're coming in here. Gotta make sure that we remember where we're focusing on. Okay, so there are some crazy properties to limits. But I'm not going to actually make you write those property limits. Let's see if we can use the property limits. Long story short, with limits, if we can take limits of pieces, then we can actually take limits of combinations of those functions. If we can take limits of, say, a function f at a certain point, and the limit as x approaches that same certain point of g, then I can put these two together with addition, subtraction, multiplication, multiplication by a constant, division, and I can actually use their individual limits to solve. Let me show you what I mean. And I want you to write this down. This is based on the properties. You can find the properties in your book. We'll write them down next year in our notes, but not right now. So we're given two different individual limits. If you guys notice, are they operating the same, aka is x approaching c for both? Yes. So since the limit is operating the same way, x is approaching c for both, then I can go ahead and answer as the limit as x approaches c and combine the two in different ways. So, therefore, for letter A, as you guys can tell from up above, we have two clues. We don't know the function, what he looks like. We don't even know his equation. We don't even know what c is, but we do know that the limit of is 3 of f, and the limit is 6 of g as x approaches c for both. So what do you think we're going to answer for letter A when it's asking the limit of negative 2 times g? Times positive 6, but yeah. Negative 12, it's as easy as that. In a sense, we can pull the negative 2 out of the limit. We can take the limit of what remains, which we know to be 6, so we can plug and chug. How about for letter B? 9. It's as easy as. Letter C? Letter D is talking about the property with the composition of functions, but it is as easy as you're thinking. The answer would be. Well, there's not really a way to simplify that one, huh? So even if we don't have a graph and we don't have an equation, if we have some clues, we can actually make more deductions than we think. That's based on properties of limits. Without going too deep into the properties or having to write them down, you don't have to memorize them. The question is, can we use them? You guys ready for the most fun section?
Good. Excited.
Section as in the piece of 12.1. Did you guys notice a second ago how it was like, hey, the limit is approaching the point that's actually there? And we used the plugging in trick in order to say what it actually was because my graph was very approximate. You can always do that with well-behaved functions. And it doesn't have to be well-behaved everywhere, just well-behaved at the point that we're looking at. Not that we're encouraging hypocrisy, but well-behaved at the point that we're looking at is all that we're caring about because the limit as x approaches c, we're caring what's going on around c, very zoomed in, focused on c itself. If, for a well-behaved function like, I'm giving you some examples, polynomials, linear functions, quadratic functions, cubic functions, quintic functions, polynomials, rationals, numerators, denominators, are well-behaved everywhere but when the denominator is 0. It's not well-behaved when the denominator is 0. Exponentials, but that domain is all real numbers. And any of the other ones with limited domains, ln's, square roots, trig functions, they're well-behaved everywhere but they're discontinuities. The ones that are not well-behaved are piecewise functions. Those little sneaky devils are something else. But almost every other function is well-behaved everywhere but their discontinuities. If you guys notice, as a shortcut to finding a limit as x approaches c, even though we are only concerned about the approach, a shortcut for well-behaved functions is the limit will be exactly what the point says it is. Because the function will be going towards the point that was already there. So we can just plug it in, plug it in. Letter R are some qualifications will be functional, not at discontinuities. But, can you do some limits? How many limits would you say we've done today? 4 or 5. We have literally, what, 60 seconds left of class? We'll finish 3. How on earth am I going to expect you to do 6 different limits in those 60 seconds?
Oh, with the
Plug it in, plug it in. How do you limit as x approaches 4 of x squared? If you guys get in the graph and zoom in, it's going to be the point that's there, 16. How are we going to do for this one? See how limits get fun. How about C? Pi is 180. Same thing as 0. And tangent of 0 is?
square root of
0 over pi is 0. Square root of 9 is 3. Pi times cosine of pi. What's cosine of pi? -1. 3 plus 4. Stop plus! Woo, we got 6 done in 65 seconds. Bye, cool kids. I'll see you later. Have fun with this homework. If you do on Monday, we are officially done. Oh, that's just really cool example. 10 seconds. Bye, all. Thievery.
Jesse, you guys were awesome yesterday. Good morning and evening. I love you. Hey, you came. I'm glad.